Welcome to this coding problem walkthrough. Today, we'll be tackling LeetCode problem number 541, titled Reverse String 2. This problem is a great exercise in string manipulation and developing efficient solutions. Let's dive in and explore the approaches to solving it. In this problem, we're tasked with transforming a given string s based on an integer k. The transformation involves reversing specific portions of the string. Starting from the beginning of the string, you reverse the first k characters within every segment of 2k characters. If the remaining characters are fewer than k, you reverse all of them. On the other hand, if the remaining characters are between k and 2k, you reverse the first k characters and leave the rest as they are. The goal is to return the modified string after applying these rules. The input consists of a string s, made up of lowercase English letters, and an integer k, both of which fall within the specified constraints. Let's explore some examples to better understand this transformation process. For the first example, we are given the input string s equals abcdefg and k equals 2. The string is divided into segments of 2k equals 4 characters, resulting in the segments abcd and f. For the first segment, abcd, we reverse the first k equals 2 characters, turning ab into ba, which gives us backed. For the second segment ef, we reverse the first k equals 2 characters again, turning ef into fe, resulting in feg. Combining the modified segments, the final output is backed feg. This demonstrates how the transformation is applied in chunks of 2k characters. In the second example, the input string is s equals abcdef and k equals 3. Here, the string length matches exactly one segment of 2k equals 6 characters. For this segment, we reverse the first k equals 3 characters, turning abc into cba, while leaving the remaining part, def, unchanged. The final output is kbadef. This shows how the rules are applied when the string length aligns perfectly with a segment of 2k characters. Now consider the third example, where s equals a and k equals 2. Since the string has fewer than k characters, we simply reverse all of them. However, as there is only one character, the output remains a. Finally, let's review some constraints and edge cases to clarify the behavior of the solution. The string length is guaranteed to be between 1 and 10,000 characters, and the value of k also ranges from 1 to 10,000. The string consists only of lowercase English letters. For edge cases, if k is greater than or equal to the length of the string, the entire string is reversed. If k equals 1, the string remains unchanged because reversing the first character of each segment has no effect. Additionally, if the string length isn't a multiple of 2k, the remaining characters at the end are handled by reversing the first k characters and leaving the rest as is. These rules ensure that the transformation is applied consistently, regardless of the input. To solve this problem, one straightforward approach is the brute force method. The idea here is to process the string in chunks of 2k characters. For each chunk, we reverse the first k characters and leave the remaining characters unchanged. This can be accomplished using Python's slicing operations, which allow us to easily reverse and append portions of the string. The algorithm is simple: traverse the string in steps of 2k, reverse the first k characters in each segment, and handle any edge cases where fewer than k characters remain at the end of the string. In terms of efficiency, this method has a time complexity of O(n), as every character in the string is processed exactly once. However, the space complexity is O(n), because slicing and concatenating strings results in the creation of new string objects. While this approach is easy to implement and works well for small inputs, it becomes less practical for larger strings due to its memory overhead. One drawback of the brute force approach is its inefficiency in terms of memory usage. Each slicing operation creates a new string, and concatenating strings repeatedly can also slow down the process. To address these limitations, we can consider an optimized in-place approach. The key idea here is to modify the string directly instead of creating new strings. Since Python strings are immutable, we first convert the string into a list of characters, which allows in-place modification. From there, we traverse the list in steps of 2k and reverse the first k characters directly within the list. After processing all the chunks, we convert the list back to a string and return the result. This method retains the same time complexity of O(n), since every character is processed once, but it significantly reduces the space complexity to 1, as no additional strings are created during the process. This makes it much more memory efficient, especially for larger inputs. The optimized in-place approach has several advantages. First, it eliminates the memory overhead associated with creating new strings, making it highly space efficient. Additionally, by avoiding repeated slicing and concatenation operations, the algorithm achieves better performance for large inputs. However, the trade-off is that this method is slightly more complex to implement compared to the brute force approach. Another alternative is the recursive approach, which offers an elegant solution by processing the string chunk by chunk. The recursive method works by reversing the first k characters of each 2k segment and then calling itself on the remaining portion of the string. For the base case, if the string has fewer than k characters, we simply reverse the entire string. While this approach is concise and easy to understand for small inputs, it introduces additional overhead due to recursive function calls, which increases the space complexity to n. The recursive approach also has a significant drawback for large inputs. As recursion relies on the call stack, it risks stack overflow when processing very large strings. This makes it an impractical choice for real-world scenarios with high input sizes. After evaluating all three methods, the optimized in-place approach stands out as the best solution. The brute force method, while simple, is not memory efficient due to the creation of new strings during slicing and concatenation. The recursive solution, though elegant, is unsuitable for large inputs because of the stack memory limitations. In contrast, the in-place approach strikes an ideal balance between efficiency and complexity. By directly modifying the string as a list, it avoids the overhead of creating new strings while maintaining a time complexity of n. Additionally, its space complexity of 1 ensures that it handles large inputs with minimal memory usage. In summary, this problem requires reversing specific portions of the string, which makes in-place modification a natural choice to optimize space usage. While string slicing in Python is convenient, it is inefficient for large inputs because it creates new string objects. Similarly, recursive methods, though concise and intuitive, are not practical for large inputs due to the risk of stack overflow and the additional space required for recursive calls. The in-place approach, despite being slightly more complex to implement, offers the best performance and memory efficiency. It combines an optimal time complexity of n with a minimal space complexity of 1, making it the most suitable strategy for solving this problem effectively, especially when working with large datasets. To solve the problem of reversing segments of a string based on the constraints, we need to break it down into manageable steps. The task involves reversing the first k characters for every 2k characters in the string. For example, if there are fewer than k characters left in the string, we reverse all of them. If there are between k and 2k characters left, we reverse the first k characters and leave the rest unchanged. To begin, we first need to understand the input and constraints. The input consists of a string s and an integer k, where k is guaranteed to be a positive number. With this setup in mind, we initialize an empty result string to store the transformed output. Then, we use a loop to process the string in chunks of 2k, iterating from the start of the string to the end in increments of 2k. This way, we systematically address each section of the string as required by the problem statement. Now, within each chunk of 2k characters, we begin by extracting a substring from the current index I to I plus 2k. This chunk is then split into two parts, the first k characters and the next k characters, if they exist. The first k characters are reversed using Python's slicing operation, ::-1, which provides a simple and efficient way to reverse substrings. This reversed portion is appended to the result string. Then, if there are any remaining characters in the chunk representing the next k characters, these are directly appended to the result without any modifications. It's important to carefully handle edge cases, such as when the remaining characters at the end of the string are fewer than k, in which case we reverse all of them. Alternatively, if the remaining characters are between k and 2k, we reverse the first k and append the rest unchanged. Once all chunks are processed, the final concatenated result string is returned. The logic behind iterating in chunks of 2k is rooted in the problem's requirements. By dividing the string into fixed sections of 2k, we ensure that the operations are performed in a structured and consistent manner, simplifying the implementation. Python slicing operations, such as ::-1, are particularly effective here as they allow us to reverse substrings efficiently without relying on nested loops, keeping the algorithm straightforward. Proper handling of edge cases is also critical to ensure correctness. For instance, when the string is shorter than k, we simply reverse the entire string. If the string length falls between k and 2k, we reverse only the first k characters while leaving the rest intact. For empty strings, the function directly returns an empty result. These small but important considerations ensure that the solution is robust and handles all possible inputs gracefully. The problem primarily deals with string manipulation, where strings in Python are immutable. This means that any slicing or modification creates a new string. While this is suitable for the problem's constraints, we can optimize concatenation by using a list to collect the process chunks. Once all chunks are ready, a single .join operation can efficiently merge them into the final result, avoiding excessive memory reallocation. When analyzing the time complexity, the loop processes the string in steps of 2k. For each chunk, slicing and concatenation are O(k) operations. As a result, the overall time complexity is O(n), where n is the length of the string. The space complexity is also O(n), due to the storage required for the result string. This combination of linear time and space complexity ensures that the algorithm is efficient and scalable for large input sizes. This solution implements the algorithm to reverse the first k characters in every 2k chunk of the input string s. We start by initializing an empty list result to collect the transformed chunks of the string. The main logic involves iterating over the string in steps of 2k using a for loop. Each iteration processes a single chunk of length 2k, or less, if at the end of the string. Within each chunk, the first k characters are reversed using slicing with ::1. These reversed characters are added to the result list. Then, the next k characters, if present, are directly appended to result without modification. Finally, after processing all chunks, the result list is joined into a single string using .join result, which is returned as the final output. This approach ensures that the transformation adheres to the problem's constraints while maintaining an efficient O(n) runtime complexity, where n is the length of the string s. This is the Java implementation of LeetCode problem number 541, reverse string 2, which mirrors the provided Python logic. It uses Java's string builder for efficient string manipulation and constructs the result by iterating over the string in chunks of 2k. Key differences include explicit type declarations and Java-specific methods like substring and string builder.reverse. This approach ensures clarity and efficiency while maintaining the same functionality as the Python solution. To solve the problem, we process the string in chunks of 2k characters at a time, where k is the number of characters we reverse in each chunk. For the input s equals abcdfg and k equals 2, we initialize an empty list called result to store the process chunks. First, we take the chunk s, 0:4 equals abcd. In this chunk, the first two characters are reversed to get ba, and the next two characters cd are added as is. Combining both gives backed, which we append to result. Next, we process the chunk s, for :8 equals fk. Here, we reverse the first two characters ef to get fe, and since only one character g remains, we append it directly. Adding this to result gives result equals ba, cd, fe, g. Finally, by joining all the elements of result, we produce the output string backfeg. Now, let's consider the case where s equals abcdfghij and k equals 3. Again, we process the string in chunks of 2k equals 6 characters. Starting with the first chunk s, 0:6 equals abcdf, we reverse the first three characters abc to get cba, and append the next three characters def as they are. Adding this to result gives result equals cba, def. For the second chunk s, 6:12 equals ghij, we reverse the first three characters ghi to get ig. The remaining one character j is appended directly. This updates result to result equals cba, def, ig, j. Finally, joining all parts of result gives the output string kbadfij. For the input s equals abc and k equals 4, the length of the string is shorter than 2k equals 8. Here, we take the entire string s, 0:8 equals abc as a single chunk. Since k equals 4 is greater than or equal to the length of the chunk, we reverse the entire string. Reversing ABC gives us CBA. As there are no additional characters to append, we add CBA to result, resulting in result equals CBA. Finally, joining the elements of result produces the output string CBA. To analyze the time complexity of this function, we need to break it down into its main operations. First, the loop iterates through the string in chunks of 2k, stepping from 0 to the length of the string in increments of 2k. This means the number of iterations is approximately the total length of the string divided by 2k. Within each iteration, we reverse the first k characters of the current chunk. Slicing these k characters takes k time, and reversing them also takes k, so this step contributes k per iteration. Additionally, we append the next k characters as is, which involves slicing another k characters, also taking k. Since appending a substring has negligible time complexity, this step can be considered O1. Finally, once all chunks are processed, we combine them into a single string using the join operation, which takes n, where n is the total length of the input string. These are the building blocks of the time complexity for the algorithm. Now, combining all the steps, we can calculate the total time complexity. The loop runs approximately lens divided by 2k times. For each iteration, the work includes two k operations, one for reversing and one for slicing, making the total work per iteration 2k. When we multiply the number of iterations by the work per iteration, we get lens divided by 2k multiplied by 2k, which simplifies to lens. Adding the final join operation, which is also n, does not change the overall time complexity because lens plus n still simplifies to n. Therefore, the total time complexity of the algorithm is n. Moving to space complexity, the primary contributor is the result list, which stores chunks of the string. Since the total size of the result list is equal to the length of the input string, this contributes n space. Additionally, we need to consider the temporary slices created during each iteration. When we slice the first k characters and the next k characters, these substrings occupy k space per iteration. However, since these slices are discarded after each iteration, they do not accumulate and do not contribute to the overall space complexity. Finally, the join operation creates a new string of length n, which adds n space. Combining these factors, the overall space complexity of the algorithm is n. Compared to brute force or naive approaches, which might involve repeatedly reversing substrings or performing redundant operations, the optimized solution achieves n time complexity by processing the string in chunks and minimizing unnecessary steps. The space complexity is also optimal, as it scales linearly with the input size. When analyzing the best, average, and worst cases, the algorithm maintains consistent behavior. In the best case, if the input string is small relative to k, the time complexity remains n, because the loop and join operations still scale linearly with the size of the string. In the worst case, if the input string is very long and k is small, the algorithm still processes each character only once, ensuring the time complexity is n. Similarly, the space complexity is always n, since it depends on storing the result list and the final string, which both scale linearly with the input size. To mathematically verify the big O analysis, the loop iterates lens divided by 2k times, with each iteration involving k operations. This gives lens, which is equivalent to n. Adding the join operation, which is also n, does not change the final result. Thus, the algorithm achieves optimal time and space complexities of n, making it well suited to the problem's requirements. Now, let's go over some common mistakes developers make when solving this problem and how to address them. First, incorrect chunking logic is a frequent issue. This happens when the string length isn't a multiple of 2k, and special cases like strings shorter than k or those between k and 2k are not handled properly. To fix this, you should include conditional checks to explicitly handle these partial chunks and ensure you're reversing the correct portion of the string. Next, modifying the string in place can also cause errors, especially in languages like Python or Java where strings are immutable. Instead of attempting to modify the original string, use a mutable data structure like a list in Python or a string builder in Java to build the result incrementally. Another common pitfall is off-by-one errors, which occur when the start or end indices for chunking are miscalculated. This can result in reversing the wrong part of the string or skipping characters altogether. To avoid this, carefully calculate your indices for each chunk and rigorously test edge cases. Finally, inefficient reversal is another concern. If you use nested loops or repeatedly slice and concatenate strings, it can significantly harm performance, particularly for larger inputs. Instead, aim to use efficient slicing and joining operations to keep the solution fast and scalable. Additionally, let's consider the importance of handling edge cases and interview strategies. Neglecting edge cases like empty strings, single character inputs, or very large strings can result in runtime errors or incorrect outputs. To prevent this, it's essential to test your solution with a wide variety of edge cases to ensure robustness. When approaching this problem in an interview setting, focus on identifying patterns, such as the repetitive 2K chunk structure. Breaking the problem into smaller, manageable parts not only simplifies implementation but also demonstrates strong problem-solving skills. Modularity is another key point. Writing helper functions for tasks like reversing chunks can make your code cleaner and easier to debug. Interviewers may also ask about trade-offs in your approach. For example, a straightforward brute force solution might be easier to write but less efficient for large inputs. Be prepared to discuss these trade-offs and justify your choices. Always clarify constraints with the interviewer, such as the maximum string length and the potential range of k values. Finally, practice explaining your logic clearly, emphasizing how you handle edge cases and partial chunks, as this is a critical skill in technical interviews. Now, let's explore related problems and alternative approaches that can deepen your understanding of string manipulation. Some related LeetCode problems include reverse string 2, the problem we're discussing here, reverse words in a string 3, and reverse words in a string. These problems share similar concepts, so practicing them can strengthen your skills in handling string-based challenges. In terms of alternative approaches, one option is the two-pointer technique. Instead of slicing and reversing chunks, you can use two pointers to reverse the first k characters in place. While this method reduces memory usage, it requires careful management of indices, which can make the implementation more complex. Another approach is recursive. By processing the string in 2k chunks and reversing the first k characters at each step, you can achieve an elegant and concise solution. However, recursion may lead to stack overflow for very large strings, so it's a trade-off to consider. Lastly, for Java users, an iterative approach using a string builder can make the solution straightforward. By appending reversed chunks incrementally, you can create the final result, though this method may be slightly slower due to the overhead of method calls. Each of these approaches has its strengths and weaknesses, so it's important to choose the one that best suits your specific requirements and constraints. Great job! To recap, we used a straightforward brute force approach to reverse specific segments of the string in place. This problem showcased key strategies in string manipulation and efficient iteration. Remember to practice similar problems to strengthen your understanding. Thanks for watching, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!